Keith's History of Time. Black holes. Still on black holes. Not far off finishing though, this chapter. That's pretty exciting. Keith's History of Time. So, let's continue. In 1967, however, the study of black holes was revolutionised by Werner Israel, a Canadian scientist, who was born in Berlin, brought up in South Africa, and took his doctoral degree in Ireland, Israel showed that, according to general relativity, non-rotating black holes must be very simple. They were perfectly spherical. Their size depended only on their mass, and any two such black holes with the same mass were identicals. They could, in fact, be described by a particular solution of Einstein's equation that has been known since 1917, found by Carl Schwarzschild shortly after the discovery of general relativity. I should have hurried up, I could have done that one. At first, many people, including Israel himself, argued that since black holes had to be perfectly spherical, a black hole could only form from the collapse of a perfectly spherical object. Any real star, which would never be perfectly spherical, could therefore only collapse to form a naked singularity. There was, however, a different interpretation of Israel's result, which was advocated by Roger Penrose and John Wheeler in particular. They argued that the rapid movement in a star's collapse would mean that the gravitational waves it gave off would make it even more spherical, but by the time it had settled down to a stationary state, it would be precisely spherical. According to this view, any non-rotating star, however complicated in shape and internal structure, would end up, after gravitational collapse, as a perfectly spherical black hole, whose size would depend only on its mass. Further calculations supported this view, and it soon came to be adopted generally. Israel's result dealt with a case of black holes formed from non-rotating bodies only. In 1963, Riker, a New Zealander, found a set of solutions of the equations of general relativity that described rotating black holes. These Kerr black holes rotate at a constant rate, their size and shape depending only on their mass and rate of rotation. If the rotation is zero, the black hole is perfectly round, and the solution is identical to the Schwarzschild solution. If the rotation is non-zero, the black hole bulges outward near its equator. Brackets. Just as the Earth or the Sun bulge due to their rotation. Closed brackets. And the faster it rotates, the more it bulges. So, to extend Israel's result to include rotating bodies, it was conjectured that any rotating body that collapsed to form a black hole would eventually settle down to a stationary state described by the Kerr solution. That's all for today.
Good afternoon and welcome to BBC Two, where we begin our afternoon on the seesaw with Postman Pat taking a message.
Postman Pat, Postman Pat, Postman Pat, and his black and white cat. Everybody knows his bright red van. All his friends will smile as he waves to greet them. Maybe you can never be sure. There'll be knock, ring, letters through your door. Postman Pat, Postman Pat, Postman Pat, and his black and white cat. All the birds are singing, and the day is just beginning. Pat feels he's a really happy man. Pat feels he's a really happy man. Pat feels he's a really happy man.
He's happy.
It had
Redless.
been wild and windy in Greendale.
Postman Pat's favourite